He's got a couple examples for 200 bushel corn. He's got phosphorus at 10 part per million Olsen and K at 120. You can see the recommendations there at 52 pounds of P and 60 pounds of K. Or he's got 18 part per million Olsen and 160 part per million K. And you can see the recommendations there, 0. So that transition from going from a recommendation to no recommendation is, in essence, what my challenge is to do for you all today. So the first thing we're going to talk about is phosphorus. The first half of the presentation was phosphorus. He has been looking at 35 locations around South Dakota over the last 4 growing seasons. And what he did is in fields that farmers would let him come, he put out what we call a stamp. And you can see it there on the right. It's just 4 plots, 100 pounds of P, 100 pounds of K, 25 pounds of sulfur, and a check plot. And he tried to do that at 3 or 4 locations in each field. Now, while this is not a rate study, it does give you an indication of the frequency, the probability of a response, and so forth. Because a lot of our work is very laborsome, this can be done more easily across many more sites. So you can see all the sites there in stars. Maybe some of you have worked with Jason, let him come into a field, and that's great. We thank you for that. And so we're going to talk about that as we go forward here. So on a soil report, what do you really need to know before you apply any fertilizer? Well, knowing what P extract was used is very important. And we'll talk a little bit about that. And then what was measured, the amount in the soil test. What is the likelihood of a response given the soil test on your report? And then, well, what do I do? How much should I apply? And so that's what soil fertility science has been doing since the beginning, is that type of work. And we call that calibration. We're calibrating a crop's response yield to a soil test. Okay? And that's what that's all about. And of course, depth is really closely associated related to that, because all the calibration work was done with a certain depth. And so if you come with a different depth, it doesn't fit the calibration. Okay? It's almost meaningless. But it can work if you know a good agronomist, and you can work through some of those things. So Jason, on every one of his slides, he had animations. And Anthony Bly doesn't do animations. So I left, I think, 2 slides in where there are animations, and I thought, well, I can't really take them out of there, so I just left them. But what Jason has here is a picture of a phosphorus-deficient corn plant. That's the purpling on the leaves. And he's got it sitting on top of a soil there. And you can see in that soil matrix, he's got P's all over. And that's just indicating the distribution of phosphorus throughout the soil. I just came from Crop Hour, by the way. This week was the Soil Health Crop Hour week, and we just had one today on soil microbiology. And Jim Ristow showed pictures of soil aggregates in his microscope, and then he has the ability to turn on a special light that will make phosphorus glow. And it's really cool. And so the distribution of phosphorus in all of these aggregates in the soil materials is really neat. It's way more intense than these P's on this slide, but it accomplishes the same thing. So initially we see the root growth from that small plant come out, and you see that those roots are only accessing part of the soil and only have access to some of the phosphorus, right? And then as that plant continues to grow, well, it's absorbing the phosphorus. That's why Anthony Bly doesn't do animations, right? Because I couldn't remember that the little P's go up the plant. But as the plant grows throughout the soil, it's accessing more of the soil volume, and ants can take up more of that phosphorus. So soil testing's goal is to mimic that root, right? That's the goal. Looking for or to correlate to plant available phosphorus. And then you see that phosphorus absorbed as well. So, as far as extracts, the questions are what is an extract, and why are there so many, and really does it matter which one you use? And so, like I mentioned, an extract is designed to mimic what the plant root can absorb from the soil, the phosphorus in this case. Why are there so many? There really aren't that many. There's a handful. The big players are Bray, Olson, and Malik. Dr. Bray and Kurtz. It's Bray Kurtz, but now we just say Bray. And then Dr. Olson and Dr. Malik. All soil fertility people searching for the same thing. The most optimal way to be able to predict what that plant can, we always used to say, see or absorb from the soil. It does matter which one you use, and we'll go through that a little bit more. So what Jason did is, this site right here in northeast South Dakota we're going to talk about next, but you see some of the other sites there. That was an earlier map, I think, from the first year he actually was at SDSU. Those are the ones he worked with. But at each site you can see the location of these stamps, and if you look really close on the right-hand side, there's a gravel road there, and you can see the shadows of the electrical poles out into the field. So you can kind of get an idea how far apart these stamps are. So at this first stamp, he took soil samples prior to applying phosphorus, potassium, and sulfur, and he did the measurements. And this is what he found at this stamp. The phosphorus at 0.9, the K at 120, and the sulfur at 13. And today, I'm going to probably from this point forward just talk about the phosphorus, okay? So the critical value for Bray phosphorus is 21. That's a number that's been scientifically developed out of a lot of years of work. And I was partially part of that work when I worked on campus, okay? So now if we look at the results from all four of those stamps, the first one there that I just showed you is on the upper left-hand corner, 0.9 phosphorus. Number 2 is right below it, 0.9 phosphorus. Number 3 is below that, 1 part per million phosphorus. And number 4 is the bigger one to the right, 26 part per million phosphorus. So a big variability just in the same field. Now again, these are the Bray phosphorus results, Bray P1 results, okay? So why such a big difference? Why such a big difference? And I've put the pH there as well. And so it's all about the pH. Because Bray extract is an acidic extract, and in soils with high pH, there's some calcium phosphates that the plant can't really get at, that the Bray test is not picking up. So the Olson test is a buffered test and does a better job when the pH gets higher. Here's just another look, a comparison between the Bray and the Olson. We've got pH, Bray, and Olson for each one of those stamps. And you can see the Olson is doing a better job of picking up available phosphorus in those soils compared to the Bray. And it's controlled by pH, or it's affected by pH. So now we're going to take a look at a few graphs comparing the 3 soil phosphorus tests, the Olson, the Bray, and the Malik 3 in high pH soils and lower pH soils. So on the top of this slide, we have pH is less than 7.3. This is the relationship of Olson to Bray, and you can see it's pretty good. All of those points fall along that line very well. It's not a perfect world. This is why we say anybody in soil fertility will tell you soil testing is not a perfect world. If it was a perfect world, all of those points would fall on that line. But we're working in a biological system, okay? We're trying to measure a biological system. And I said that on purpose because I'm going to allude to that a little bit in the future here. Here's Malic and Bray right here, Malic 3 phosphorus and Bray P1 phosphorus, almost 1-to-1. So you can say that Malic and Bray are the same. They're both acidic extracts for phosphorus. Both acidic extracts. And then over here is the relationship of Olsen to Malic. Well, if Bray and Malic are the same, this graph should look just like this graph, and it does. Okay? But what happens is when we go over 7.4 pH, is my pointer showing up there? It's not. It was before though, wasn't it?
I didn't see it before. Someone else said yes.
Someone else said yes. Okay. I'm pointing at this stuff and nobody can see my pointer. But anyway, I'll try to do a better job. So in the bottom part of the slide is higher pHs over 7.4. And again, same thing. Olsen to Bray comparison on the left bottom side. A scatter. There's really no relationship. And that's because at those higher pHs, we have mineral-associated P that comes into play. Okay? And when we look at the relationship between Bray and Malic, same scatter, same mess. Bottom center graph there. Same mess. But when we look at Malic to Olsen, it improves. Malic is a weaker acidic extract than Bray, just slightly different acids in the extract. So we would expect Malic to do a better job, and it does. So Dr. Malic was looking for the universal extract. He had Malic 1, Malic 2, and Malic 3. Just keep working and working and working. That's a career. That's a 40-year, maybe 50-year career. And just keep doing those things. So pH matters in the soil. Phosphorus soil extract matters. So we in South Dakota just switched to all Olsen. And, I don't know, when did Ron do that? Dr. Gelderman did that, I think, in the 90s. Just decided we're just going to run Olsen on everything. Because up to that point, if you submit a sample to a lab, if you don't tell them what extract you want to use, they're just probably going to use the cheapest one, okay? And so it's important to know these differences. And it used to be that if a sample came into the lab, the pH would dictate what extract would be used. And now I think most soil testing labs have switched to Malic 3, and because it does show to work across the range of pHs. On my farm, I've always done Olsen. I stick with Olsen. I'm going to submit my samples here, hopefully in March or April. I will select Olsen again because I want to develop trends on my farm from 5 and 10 and 15 years ago. I want to look at which direction the phosphorus test is moving. So that's why I stick with what I stick with. So it does matter what extract that you choose. Again, I explained scientists have been just searching for the best estimator, and it's dependent upon soil pH. So when soil pHs are below 7.3, 7.4, Bray and Olsen work great. Above that, Olsen is the best, and Malic 3 appears to do a decent job across all those. And at the bottom of this slide, I just put what those basic parts of that extract were. So it's a sodium bicarbonate is the Olsen extract, which is buffered at a higher pH. Bray P1 is a hydrochloric acid extract, so a stronger acid. And then you talk about Bray P2. I think some of you probably can relate to that. There's a certain lab that does both tests. And so it's even a stronger acid. It pulls out even more phosphorus. Okay? So we the soil testing world has identified that Bray P1 is better than Bray P2 at estimating phosphorus. Malic is an acetic acid weak nitric acid extract, just for your benefit on how those are different. So we go back to the soil test report. There in the red box, we have Olson 12 part per million. So now that we have that, what is the likelihood that the crop will respond to fertilization at 12 part per million? And then what rate should be applied? So if we think about our soil test levels, a very low, medium, high, and very high. Olson phosphorus has the ranges in ppm that fit into each one of those categories. Okay, you can see that from on the left-hand side there. 0 to 3 is very low, up to over 16 is very high. Bray P is slightly higher because it's an acidic extract. It pulls more P out. But again, this is a calibration. It's nothing magical about the magnitude of the number. It's how well does the calibration work to your crop response to applied P. That's what it's all about. And so in some regards, 25 and 30 years ago, we were having conversations like the old soil test reports didn't even put the number on it because it made it confusing. They just put the category, oh, you're low, or you're high, or you're very high. And that was easier to understand. And when the numbers were put on, then we seen all this arguing. Oh, Bray's better than Olson. Bray pulls out more P. No, that's not the story, okay? That's not the true story of how those should be used. But what's really important is the probability of a response to these soil test categories. When you're in the very low category, there's an 80% response to getting a increase in yield with applied phosphorus. And I suppose this is the point, Jason, I should say, that there's currently a work being done in no-till. I know this is a no-till conference, but more soil health, regenerative type soil situations that show that optimal crop yields are coming even when soil tests are low and very low. And why I brought up the crop hour we just had is soil biology is really what's driving that, okay? Mycorrhizae fungi is what's driving that. And I think I'm also going to say today that, I almost spent a whole career working on things like this. And it wasn't until probably last night or yesterday afternoon, it kind of came to me that phosphorus research work has stacked the deck for phosphorus. Jason's kind of laughing. Am I going out there too far? Because as you apply more phosphorus to the soil, and Drs. Osborne and Lehman with ARS and others that I'm probably not aware of have published papers that have shown that phosphorus application to the soil reduce mycorrhizae fungi activity. And the mycorrhizae fungi are important for phosphorus absorption as well as water and other nutrients. And so the more phosphorus you put on, the less mycorrhizae fungi you have there, and so you become more reliant on applied phosphorus. Does that make sense? So in the past, I have said I'm an inorganic agronomist trained at SDSU, and there's several in the room. I'm proud to say that. I think I got a good education there. But I'm trying to become an organic agronomist, and it's hard because there isn't a lot known about it, and it's cutting edge. It's the beginning of the future, I think. And I asked Jim Ristow this morning, do you think there will be a day when an agronomist has a microscope and is looking at the biology in the soil to help predict whether this soil is more dependent on synthetic fertilizer additions or is more on the organic side or whatever that might be? And he agreed with me, and I have that vision too. It's just not here. But it's being worked on. If you are interested in this, just just go home and Google Dr. James White, Rutgers University. His whole research team is focusing on the interaction of plants and biology and nutrient uptake. The rhizophagy cycle, Jim said, was discovered in Australia 10 years ago. Dr. White is working on this. It's really important. It's really important. So, having said what I said, we're going to continue with this inorganic soil nutrient presentation, okay, with all that said. So if we look at a graph where we have soil test P on the bottom, 0 on the left, 20, 24, 8 on the right, and we have corn response frequency on the left, or the y-axis, the vertical axis, you can see that the frequency is a lot higher if soil test P is very low. And that decreases as soil test phosphorus increases. So hence, we have these developed categories of very low, low, medium, high, and very high. That's phosphorus calibration research. That's the essence of it right there. So we're going to look at a graph, and I think, yep. Man, I was deleting a lot of animations yesterday. Wow, it just was unbelievable. I think I missed these. But anyway, this is the results of all of those stamps that Jason's did, because it is a frequency of response work, okay? 1 phosphorus rate, what is the frequency of response? That stamp study cannot answer the question, what rate to apply. It can't do that. So this is how you use that data. And so you develop 3 categories. A set of that data where the yield was raised, a set of that data where the yield was lowered, and a set of that data where it remained constant compared to the check plot. And you plot those across soil test phosphorus. And that's basically what he did here. And how you use this soil fertility calibration method is you look where the lines generally intersect. And that's right at 20 part per million Olsen phosphorus. So if you had no other data, if you were just brand new in South Dakota and there were no phosphorus soil test recommendations, and you had to do quick work because you had people that wanted to know, this is probably what you would do to get a quick answer. And so the sufficiency level would be 20. Now, it does not answer the question, how much to apply. We probably could ascertain that as you got lower phosphorus, you would need more than as you got closer to 20. We probably could do that, but still, we don't know. All we know is it took 100 pounds of P to get to that 20 part per million sufficiency level. So above 20, there's no need to put on any more phosphorus. Okay, so that's one method to determine. So another approach is to use what we call the relative yield approach, where we put out a rate study as shown in this slide. Along the left-hand slide, you see 4 replicates in blue there, right? And then across the top red boxes, you see phosphorus rates. Now, they're not all shown in each rep, but they're randomized throughout that rep. And you've got 4 checks, 4 30s, 4 60s, and so forth. And then what you do is develop a yield response curve, which is on the right there, and you plot all of the yield data across phosphorus rate. And you look to see if there's a yield trend. And at this site, there's a yield trend, and it looks like 71 pounds of phosphorus, indicated by the green line, gives you what we call maximum yield. There's no further crop yield response beyond that point, okay, to this applied phosphorus. So we take this data and we do a bunch of these. Okay, can you see that it's a step further down the road from the postage stamp? Can you see that it's a lot more work? There's 25 plots here, or no, there's 30 plots here, and you do this at a number of sites, you've got a magnitude of way more plots than you have with the postage stamp. okay? So carry this down the road a little further. We do some analysis here. What was the yield with no phosphorus applied? It was 41 bushels. What was the yield at our maximum yield? It was 76 bushels. Okay, right there. Our relative yield is 41 divided by 76. And so the relative yield is 54. Okay. The check yield was 54% of the max yield. And the reason we use relative yield is because looky here, this is a corn site and the max yield is 76 bushels per acre. Yesterday, I wanted to just pull whatever hair I had left out, because it's like, we don't show our stakeholders poor yields, do we? You know? And I got to think of, why is he doing this? Well, he's doing it because it shows you how you can take a poor yielding site and calculate a relative response, right? And combine it with a average yielding site and a high yielding site, and you can combine all this data together. And that's how you do that. Okay, so I think the purpose he was showing this is because of that. I'm going to hope that's the reason. I really didn't want to bother him that much, okay? I really didn't want to bother him. But anyway, that's how you do this, and you do this at a bunch of places and a bunch of environments and a bunch of management. And if you want to know what it's after wheat or after soybeans or corn on corn or no-till or conventional till or strip till or whatever, then this monster grows. It gets bigger and bigger, and pretty soon, well, we're one deep the way it is at the land grant, okay, one deep. So can you imagine why we do the things that we do? That's why we do that. So there is the change in yield, of course, 35 bushels. So again, I kind of explained this. We're just striving to identify a critical level by developing all these relative yield numbers. And here they are. So we did a bunch of these studies, and I think I've showed the graph from the old data that we had to support our 16 ppm on Olson. Jason did some more. He's the new guy, right? I mean, I don't want to say the old guy can't tell him anything, but when you're young, I mean, you want to just do your own way, right? Do your own thing, and I get that. And so what we have here is all of those points, relative yield on the y-axis, and plotted, and you can see at the beginning or the left-hand side, those scatter of plots are starting to go up, and then at some point they'll level off, and then they go flat. And so what Jason's job is, and what he has learned well, is how do you take this data and what do you do with it? Make it meaningful. And so in very small print in the upper right-hand corner, we have a quadratic plot of that data. We have a linear plateau plot of that data. We have a Kate Nelson, again, two scientists, Kate and Nelson. And then there's the average, okay? So Jason took all of those models and applied it to this data, and then you can see the points there of where that curve bends flat. He's drawn the red and the purple and the green line down, and those would be the points that are indicating a sufficiency level for that certain kind of analysis. They're all different. This isn't push button stuff, right? We're dealing with a biological system. So they're all different. So the next slide, we've kind of summarized those. The linear plateau critical value is 16, the quadratic's 20, the Kate Nelson 16, the average is 17. The confidence intervals are kind of interesting, the lower and the upper, right? Some are narrower, some are wider, but the average is 13 to 22, okay? Again, soil testing is not a perfect science. It can't be. It cannot be. There's variability in everything we do. And location is really important. And Jason put these in here, I'm guessing, from thinking about it a little bit, is he's got the East Coast, K on soybean, he's got Arkansas, K on soybean, and then he's got Upper Midwest, P on corn. And Dr. Franzen from NDSU, who's retiring in June, a longtime soil fertility researcher, soil scientist, proponent of soil health. I believe that. I've heard him speak about that. He did that. He spoke here, I think, about how much soil North Dakota has lost. I can't remember if that. But really, all soil fertility is local. It really is. And that's what SDSU has tried to do is do enough of these around the state and encompass the different management that you do. And it's only as good as that process. So here's a good example. You can see the critical level for K in the East Coast is, if I draw the line down, it's about 55 to 60. If you do it for K on soybeans in Arkansas, it's probably 130, 140. So you can't take the recommendations from the East Coast and apply them to the Upper Midwest. And there are folks that have tried to do that. Okay? It's been done. Same way with Arkansas. It's all local. So the importance of, I'm going to get on my land grant university kick here, but that's why we have a land grant in every state. Okay? That's why we do. And then you can see the P on corn from 4 states put together. And I don't know how that was done, but it was done. And it's pointing at that 15 area, 15, 16. Personally, on my farm, I manage for 12. If I can average 12, I'm happy. Why do you do that, Anthony? Well, I'm kind of conservative. See, it's all local, right? It's all local. Okay. Okay, so now let's look in the change in the yield approach. From what he has done with those rate studies. You can see here's the data. It is elevated a little bit. It's indicating that 16 is not the number. It's probably more like 22 or to 24. Here you can see that coming down there around, he's got it around 22. It kind of looks like 23, but whatever. The math is the math, okay? So you can look at the critical value approach and that's what you get. But we're still, there's the 16 that we're at, and with any fertilizer recommendation, there's a probability, as I mentioned, there's a % chance of a response. If you go back to that one graph where the lines intersected and came down, if you think every time you apply phosphorus you're going to get a yield response, well, I got something new for you. That doesn't happen, okay? It doesn't happen. I wished it would be that easy, the push-button approach, but it's not. So what Jason has done here is he's done it at 5 bushels on 200 bushel corn, okay? That's a small %. So are you willing to take that chance? And I think it's a pretty good chance. Because it's a very small chance you'll get a response above that point. So a lot of this determining a critical level is, you use the fancy math and everything, but you still have to come down to making a decision. What am I going to say? What am I going to say? And how much risk do I want our stakeholders to take? Right? You can't let your personal conservatism or liberalism get in the way. You have to think about, in general, everybody that's out there and how they're doing it. So the critical value approach could be that. So if we summarize these, frequency approach was 20 ppm, the relative yield was 16 ppm, and the yield difference approach was 22 ppm. So there's kind of the decision he's made is it's still 16. He can't fault you for going to 20. But again, I think Jason's doesn't fully realize that there's documents out there that are hinging on our documents, and I think it needs to be one number, but we'll have that conversation too. But anyway, with a 5% or 5 bushel per acre response at 16 part per million, that's the risk you're taking if you use 16. according to the data he has. So the accuracy of Olson phosphorus is 68%, and when he added in, he's doing other work with these stamps and all this stuff. You know, we just don't measure soil P, he's measuring the whole toolbox there. He measured CEC and clay, and when those were added to the model, along with respiration, that increased 6%, up to 74%. So there is some hope that other soil indicators could be used. But do you want to use them? Most people want simplicity, right? You have to pay for all those things. Soil respiration costs more. CEC is relatively on every report now, so not all that big of a deal. Clay, going to have the clay analyzed? That's going to cost more. Going to do that on all the grids in your field? Probably not. Go ahead, Jim.
How do you measure soil respiration?
That would be that Solvita test. Yep, that would be that, I'm pretty sure. Okay, so I'm done with phosphorus. Any questions? I'm probably out of time. Okay, I'll keep going. MRTN versus yield goal on nitrogen. Here's all the sites that he studied: 32 conventional, 13 no-till, 35 after soybeans, 10 after wheat or corn or other crops. Basically, I added this in here. This is what we're all after in the soil health world. We're all after more for less. This is one of those sites. The economic optimum nitrogen rate, EORN, or however you want to say, is 55 pounds there, indicated by that arrow coming down. But this site was 26 years no-till at 5.4% organic matter. And I got a note there. We can't forget about the carbon. And Dwayne paved the way for that in this area. When he first said that, I don't know how many years ago it was, I thought, what the heck? I first thought about getting a fertilizer spreader and spreading carbon. And then I had to bring my brain back to reality and go, oh yeah, okay, I know what he's talking about now. It's all about the carbon, okay? It just is. So these are all the sites that he's done. You can see there that the economic optimum nitrogen rate varies from 0. There's several sites at 0 all the way up to 200, okay? And this is another example why soil testing is not perfect, okay? But the zeros, I personally know something about them. And I would categorize them as our leading soil health producers in the state. Those that have done no-till, those that have done crop rotations, those that have done cover crops, those that have put livestock out there, those that are following the soil health principles. I do know that about them. And that's not to say every year it'll be 0 on their farm. Don't even go there. That is not the way to apply this, because some years those systems on those farms will need some nitrogen. But that's the hard part for those people at 0. Okay? They're probably still applying nitrogen. In fact, I know they are. I know they are. We just got to give them the tools to be able to predict when they don't need it. And that's where I think that microscope is going to come in someday. Okay, keep going here. Shut up and keep going. So if we look at a location influence, there we have our no-till and conventional till. If we separate those out, look at them, the economic optimum nitrogen rates are slightly higher for no-till. If we look at the soybean versus cereal grain, we know we need more N after wheat than we do after soybeans. There's the so-called legume credit that we have. And then east versus west. The wetter climates, higher productivity, need more N than the drier western climates. Okay? That's how we'd sort that out. So there's a couple different ways to look at nitrogen recommendations. Yield goal, there's the equation. He doesn't have it at 1.0, but it has been changed 1.0 per bushel of yield goal. And then we have the maximum return approach, so the two approaches. So here's the yield goal approach. It has yield goal, coefficient, what you measured in the top 2 feet, the legume credit, and a standing no-till debit. And I would say that is for emerging brand new no-till fields. As you get longer down the trail, that goes away. And Sarah Bowder's research shows that. Okay, that was done at the Southeast Farm. So how accurate are we? So if we look at all those sites, and now we know after the fact what the right end rate was at that site. Before doing that work, we had no idea. So we put out all those rates. We can calculate the amount of N it took to maximize yield. So that's what we see in the blue at each one of those sites. And then at the red is what the SDSU recommendation would have been at 1.2 pounds of N per bushel. So you look at the differences between the red bars and the blue bars, and you can see there's some error there. Again, soil testing is not a perfect world. We're working with a biological system under the influence of a climate. Okay? Totally awesome. So 1.2 is overestimating by an average of 76 pounds of N per acre. 76 pounds per N per acre. And I got to admit, on my farm, I quit following SDSU recommendations. It says right there, I work for SDSU. Because I knew on my farm that I didn't need that much N. Again, soil fertility is all local. You need to put out a strip in some of your fields. You need to try to do something. You got the yield monitors. You got the ability now to do that. You need to do that. Okay? So we knew something had to be changed, and I'm not trying to pat myself on the back, but I had data prior to Jason arriving, and I was showing that it's probably 1, but I officially could not change it because I don't have PhD behind my name. Okay? And that's okay. That's okay. But I can still show the evidence and the data and show that it should have been 1. Well, it's been changed to 1. Okay, so can we improve the 1.2? Obviously, we can improve the 1.2. We can drop that average down, and it would be better off for all those that are still using the 1.2. But quite frankly, in talking to a lot of farmers and agronomists, hardly anybody was using 1.2. The only people using 1.2 were the people that had the rules and laws, right? The people that regulated, like the large animal feeding operations, they had to follow 1.2. And if you did a program with NRCS, you had to follow 1.2. But as I talked to folks, hardly anybody was using 1.2. So it really didn't bother me all that much. I didn't think farmers were losing broad acres of money putting on too much nitrogen, right? Because I think they'd figured this out already. Okay, so here's a comparison of what 1.2, 1 and 0.8 would look like. So if you go to 0.8, a lot of those orange, yellow bars are below 0. So that means that they're underestimating the amount of nitrogen that is required. So 1 is doing the best job, as you can see right here. It still is 13 bushels on average higher than the optimal nitrogen rate at these points, but I think that's a good place to be. You don't want to be under. You don't want to be losing or leaving yield on the table every year. So in the past, it's been as high as 1.45 in 1975. That's what it was. And then in 82, it went to 1.3, and in 91, it went to 1.2, and there's where it stuck. There's where it stuck. For a number of reasons I could share with you, but it might get me fired, so I better keep my mouth shut. But it's stuck at 1.2. And so Jason came along, soil fertility guy, he changed it to 1.0. So thankfully that's been done. So does the economic optimum nitrogen rate really relate to yield? Well, here's the relationship. Those are all the optimum N rates for those sites, and that's yield. And so you'd say it's very poor. And it is. It is very poor, but the trend is there. Again, I would like to say all soil fertility is local. Try to do something on your farm. So this has been changed to 1. We've lowered the average recommendation from 105 to 76, but what about the economics? What about the economics? Okay, I mentioned the maximum return to N. That's what it's all about. It's tying the price of nitrogen and the price of corn to the nitrogen rate. I still have a big problem with this in my mind because I'm a farmer. I paid for a lot of fertilizer before the first of the year, and I haven't sold 1 bushel of corn. Right? You make certain decisions on your purchases because of taxes, price of fertilizer, all those things. And you make certain decisions on marketing corn because of a lot of things, right? Market reports, what's it like in South America, blah, 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 blah. So for the MRTN approach to work, those price of nitrogen and the price of corn really need to be linked. For every pound of N you buy, you probably should sell a bushel of corn. But in reality, that's not going to happen. That's not going to happen. But so we've got this method, and so what we're looking at here is that blue line is really an expensive price of N. If you look at 100 rate there of nitrogen and go up, that's $100 per acre. That's $1 per pound of N. Did that happen? Yeah, it did. Did you forget? I mean, prices have thankfully come down, and I hope they go down further. But what we do is we combine the price of nitrogen and the value of the corn, and we come up with the red line. That's our nitrogen rate. And then we look at a probability above and below that, and so the nitrogen rate here would be 75 pounds of N per acre. Now, how this works is there's one MRTN for South Dakota. Or, as Jason gets more data, there's one MRTN for eastern South Dakota. And then maybe the James River Valley, and then the central and the west. Right? More data makes this more powerful. So the yield approach, where we had your actual soil test from your field or your grid or your zone, we knew what the nitrate was there. You know what the yields that you've received in the past. That's your yield goal. It's not 400 bushels. It's what you've been doing there plus 5 or 10% more. That's a yield goal. And that has important in that equation in the calculator method. Because if you just put 300 bushels or 250 bushels and you got that one time in the last 10 years, you're overdoing nitrogen terribly. It's got to be the yield goal. Okay? It's not about the yield you want, it's about the yield you can get. That's what it's about. That's yield goal. Okay? Plus a little more because we know yield trends are going up. So that's how that works. So MRTN. So if we look at all of it, it's 97. If we look at no-till, it's 94. Or excuse me, till it's 94, no-till 97. We could also look at the rotation, the carbon rotations, corn or wheat, 98, corn after soybeans, 95, and then the location. I think this is the most significant, eastern 102, central 60. Those rates, I think, are a lot lower than what's typically being done. I think they are. So can you imagine a world where SDSU puts, we're going to go to the MRTN approach, and these are your rates, and then you're in CSP or you're in some other program, and you got to follow this. It gives you less flexibility. I'm being a little hard on MRTN, but for certain reasons. I don't think we have enough data yet to fully move to that, but again, I don't make those big decisions. So anyway, here's what we did. I had a number of sites in all of these areas here. We're lacking on the west. Here is the South Dakota MRTN accuracy for the whole state. No, for each individual site. Sorry, I lost it there a little bit. And then the East and Central MRTN accuracy. So it's really plus or minus 65 pounds of N in the East. You want that? You want that huge of a range? I don't. I don't want that. 45 in the Central. So let's add MRTN into the new data. Here's that data again. I just showed you. What he's trying to show here is the sites that are under fertilized, the sites that are kind of hitting, and then the ones that are totally over fertilized. So if we look at all them sites, what he's showing here is more data makes MRTN more robust. And that's a true statement. You got to have a lot of data to make MRTN even work. And do you jump into Minnesota or Iowa and use theirs? I wouldn't do that. I wouldn't do that at all. It's got to be local. So this shows that MRTN is more accurate. Those MRTNs, or the variability comes down when we add more data. And so he's just got 4 years of data to do that with. So let's compare the accuracies of these two systems. Here we have the yield goal approach in the red bar with its error. The one coefficient there it was the red bar, so 1 pound of N per bushel of yield goal. MRTN for the whole state of South Dakota. For the east in the green, and look at there, it's almost perfect. So I guess we should all just start applying a lot less N, and I think you have. And then the N recommendation minus the N needed is there in the purple. So you can look at the different variabilities that are there. So with that, I'm done. And I've probably used way too much time. And I hope I've done Jason's presentation justice. I've put my own flair to it, made it what I think I should make it. So thank you for your time.